case, when process 1 is there and it finishes, process 3 is there and it finishes, and process 4 is left, a very big button, process 2 and process 4 are left, then what is happening in these parts of memory? Well, basically there is something that gets allocated. Now let us say that instead of process 1, when process 1 is finished, process 5, another process comes in. So when process 5 comes in, it is allocated this part of memory, let's say. Now here, let us say that this part is occupied by a part of process 1, and you have to just give some more space. There are some functions, etc., that need some space, so give them more space. Now, especially in case of statically allocated programs, like for example our box standard C programs, which follow a static allocation of memory, all the functions must find its memory space before the execution starts. So, because we have eaten up this space, okay, so if I can draw it like so, let us say that we have a situation, but there was process 1, process 2, and process 3. Okay. Now let us say process 1 executes fully, process 3 executes fully, so process 2 is still left. This is free space, this is free space. Now let us say that a reallocation is done. What kind of reallocation? Well, process 4 comes in. Now process 4 is allocated this memory space, but this is not enough for process 4. Process 4 also needs some more memory. This is the memory that is available to you. Now process 4 also needs some more memory. Now it cannot flow into P2, that is for certain. And if you cannot have the algorithms for moving P2 to this part, then what will happen? P4's rest of the P4. So this is, let's say, P41, and we are left with, say, P42. P42 will have to be allocated here. By P41, once again, I mean the first part of process 4, and by P42, I mean the second part of process 2. So rather P42 will have to be allocated here. So that we have a memory situation where we have got one process here, part of it, another process there, which is a different process altogether, another process here, which is a part of the first process. So let us say this situation here, this is a P41, this is a P42, and inside here there is something which is the P2 process, and we are not worried about it because we are only dealing with P4 at the moment. In that case, okay, the program counter increment at x plus 2 is not going to work. Very simple, because it is going to go into P2. It is not going to work. So what do we have to do in that case? In that case, the program counter, well, who does this? The assembler does it, or the operating system does it. Whoever is managing the memory, maybe the operating system, mostly is the operating system that does it. It will load after x plus 2. It will not be PC equals to PC11, PC plus 1, but PC will actually have the address here, y. There will be reallocation, there will be no more increments, and this can be achieved with a jump instruction also. So at x plus 2, because it is going into P2, we would most probably use a jump instruction. Say jump, just jump to y. When this instruction is encountered, PC gets the value of y, and control just goes to y for further processing. Control just goes to y for further processing. So this is a situation that it ends here and now it comes back here for further, and it just skips P2, obviously, because P2 is not a part of your process 4, so it should not even touch P2. Now, yeah, exactly, Suman. I mean, exactly, Divya. Who obviously is a very obvious question, that who is going to give the jump instruction? As I was saying, the jump instruction is going to be given by the program that you're using or the operating system who's managing the memory. There, these exclusive jump instructions will be written with your program. When it will be compiled or when it will be assembled, it will be there. It will have an indication, okay, that it is finishing here and P2 is there, so we must use some more memory if P2 cannot be reallocated. Mind you, modern algorithms are very flexible. What they do is they're dynamic also. So what they do is they just shift P2 to this part so that you have a continuous part of memory. Continuous memory is always very good for execution because it is easier to handle. But let us say you cannot do that. So in that case, a jump instruction becomes necessary. Who issues this jump instruction? As I said, once again, let me repeat myself. The operating system may do that for you. The reallocation loader, the loader is basically a program that brings your program from the into the working memory, that is into the RAM or that part of ROM with which you're working. Where does it bring it from? It brings it from either the hard disk or the optical drives or the flash drive or some other secondary medium, or it may even bring it from ROM, where ROM is used as a device storage. It may bring it from ROM as well. So that loader might do it, and the operating system, when it allocates the memory, manages the memory, it might do it. If the user has any notion, if the programmer has any notion that it'll have to uh, use some separate parts of memory, he will do it, but he mostly has not got it because it is running inside, so he mostly has not got any idea. Sometimes these jump instructions are issued dynamically by the operating system. Sometimes it is issued by the compiler, or the that is to say the relocation loader, more specifically, which locates the various uh, memory addresses to these functions. Obviously, jump can also be issued by programmers, but not in this case, but other cases. For example, if you have a program whereby you want to access from this part, finish it, come back to this part, you have to use jump instructions. Here, you may have used a jump. Normally, we can use something called a return. Because when the jump happens, the program state, as we discussed yesterday, is stored on the variable stack or the program state stack. We use it. And when you press return, okay, then that other stack is restored and the it carries on from the return address of the control, which is to say the line just after or the statement just after the statement where the jump occurred. This is jump that is either explicitly or implicitly used by the programmer. By explicitly, I mean he might write the jump instruction himself. Say, for example, jump OXFF00, which is nothing but jump to address FF00. OX obviously means hexadecimal. let's say that this is OXFF00. So you're jumping to this part. And if this is, let's say, OX say FE00, then this is OXFE01, let's say, and the return will happen to OX. Sorry, if this is OXFE00, and this basically will be OXFDFF. Okay, this one. The jump occurred at OXFD FDFF, and we're returning to OXFF00. So this will be a jump which is provided by the specific command return. Returning to where? Is returning to OXFE00 from here to here. And implicitly, uh, so this is explicit jump instruction. Implicitly means that if there is a program where these jumps are necessary because of memory management, as we had seen here, then the jumps may be provided by the assembler or the compiler or the interpreter. It may be provided by the operating system, okay, that is managing the memory. But those are uh, implicit. So if you have to do something, then you have to, it is implied that you have to jump somewhere and do it. So that way. I should say like this, directly or indirectly. So more indirect approach is when the compiler or the assembler does it for you, and directly the program contains jump instructions from the programmer. Both can happen. Now this jump can be of two types basically. It's an unconditional. Another one is conditional. Unconditional refers to just a jump instruction. Jump to certain point. That's it. Nothing else. But conditional just checks a condition. Okay. Just checks a condition on which it jumps. In 8085, for example, if we take this as an example, in 8085, for example 8085, we have jump, and then we have jump on the basis of the PSW, the program status word. There is a status register. Jump if it is 0, jump if it is not 0. As you can imagine, checking on the bits that indicate whether there is a 0 or whether there is a non-zero. Okay. Jump with carry, that is there is a carry, jump to this part. Jump with no carry. So jump if it is positive, jump it is if it is negative. That is based on the sign. Now the exact commands will be available to you with the 8085 uh, assembly list, assembly language, listings. This may not exactly be the instructions, but these are like this basically. So these 7 jumps and the return. So the return can also be same thing. Either it's an explicit return or a return checking on conditions. And most likely, this checking on conditions obviously is going to happen on the program status word. So return explicitly and then otherwise return let's say or return checking some condition with that is in the program status word. Just like in case of jumps, it would be return if it is zero, return if it is non-zero, return if there is a carry, return if there is no carry, etc., etc. Once again, the user may issue these commands in the program if it is within the program sequence per se, and if it is not, then at the time of assembly or compilation, the assembler or the compiler, or at the time of interpretation, the interpreter might provide these jumps into the program. It might be introduced so that the program works properly. When we are going from, say, the main function here to F, there is a jump. This to G, there is a jump. This is a return. This is a return. Okay. So these are all jumps. Jump, rather, jump, jump. This is a return. This is also a return. So jump, return, jump, return. So it will be jump, jump, and it will fold out stack wise, return, then return. Very simple. Now, so this is how we use subroutines and go between. So in one program, there are several functions. Just like that, there are several subroutines. So the functions are actually, they are basically those are uh, implemented as subroutines, obviously. Now, there's also something that when the processor is handling more than one functions, there is something called context switching. Basically, it means rather cycling between active tasks or processes. So, which is something that we showed that this T1, let's say P1, P2, P3, P4, and each of them are given a certain number of machine cycles. Then again, so basically it goes P1 served, then P2 served, then P3 served, then P4 served, then come back again to P1. And all the time this happens going from, so from say program 1 to program 2. Program 1 state is saved, okay, then program 2 state is reinstated, execution starts from where it stopped. That means you start P2 before. When you switch to P1, P2 state is saved on the stack. State means all the values of the registers at that point in time. Now, when P2 is again reinstated, P1 state is saved, P2 state is reinstated. That is, now all those variable values in the stack, they are then reinstated back into the original registers so that the computer can start working from where it left. And this is called context switching. The context in which the processor is working, that means to say the program with which. When we talk about context in case of English language uh, communication, we say in which context are you speaking. That means in what background or in what environment are you speaking, or regarding what environment are you speaking. For example, if we say we are 11 people here plus me, so that's 12 people here. So if I just say 12 people, that doesn't make any sense. To give it some sense, you have to give it some context. So, for example, in the context of 12 people going to a picnic, that's a good, that's a very good number. Now, if the context switches to say 12 people on an online class, I would say that the number is not that impressive. So, depending upon and why is the number not impressive, because there are so many other people. Obviously, if there were 12 people together, then 12 is 100% attendance, which is good, very good. But in the context that there are more than double this amount of people, number of people, then I would consider good attendance when it comes to something like 25, 26. But many of students have not joined. So we're only 12 people here, me and 11 of you from first year. So that is together 12 people. And I will not call this a good presence, a sizable presence. In fact, I would say that the percentage of people presence is appalling, if you ask me. It's like less than half. So, depending whether the context is going to a picnic or whether it's conducting a discussion, an online technical discussion, or more specifically, in the context of where the discussion is held, there are some people joining in and discussing, and there the context is 12 people out of 12 or 12 people out of 30. The opinion of the number of people present will change. Similarly, when I mean context in case of computers, I mean the context in which the processor is being kept busy, and that is actually the program environment in within which the processor is kept busy. That means to say, in very simple terms, the program which has kept the processor busy. So context switching means switching of the programs. That means it is working in one program, then shifts to another program. Now, definitely, context switching is achieved by software support, including the software, including the operating system support. But obviously, the computer, then that will have to have the they'll have to have enough mechanisms for supporting all this is context switching, jumps, returns. And what does that? Obviously the opcode, and that goes to the instruction decoder, and from the instruction decoder the proper circuits come into play. Those circuits which allow the switching, those circuits will have to be available. At the hardware level, those people who fabricate the hardware, they have to build in the circuits which will copy all the registers into the stack, which is by the way in main memory. You have to have the working memory, otherwise stack will not be implemented. It goes in there, and then when process is reinstated, we say that when we switch contexts again, come back to the previous context, and then immediately that has to be restored. Otherwise you cannot start off from where it started, you see, because all the calculations that are there, that is reflected in this program state and in the program status word. All these registers are containing the values, including the accumulator, are containing the values where you left it from. If not, then obviously you have to start again from the start of the program, which is obviously not possible. So this is one of the major issues that bugs us. How do we context switch properly when we are designing a computer architecture, and when we are using the and when we are designing the microarchitecture, that is the organization of the computer? What are the circuits that we build in and all that? This is not a subject matter of study for us. It is actually a subject matter of study for the instrumentation people and the electronics people, specifically the instrumentation people, who in outside of India, they're called computer engineers or electronic, just electronic engineers really. They are concerned with how to build the circuits, digital circuits that will make the computer work this way. Okay. Now, it's one thing, imagine there is a clock is there, the control unit is there. So inside the control unit, all this logic is there. The control matrix is there. The decoders there. The encoders are there. The multiplexers, demultiplexers, all of that are there. But to use them properly, how you can leave it to the hardware. Once the software is there, the software is obviously necessary because otherwise you cannot drive the hardware. But once you have the software, who will drive the software? The software without the hardware is once again nothing. So one needs the other. So the software engineer devises the programs knowing the computer architecture and organization. But the electronics engineers, well, I mean, at the moment it's electronics engineering. If we have biological computers, it will be the bioengineers or bio instrumentation engineers. If we have chemical computers or quantum computers, then those technologies will be used. Then those technologists who would be using or he would be building the biocomputers, who would be building the quantum computers, who would be building the chemical computers, those people, just like the electronic engineers and electrical and electronic engineers of today, they are concerned with building the circuit which can run the software engineers program. How it will go one after the other, bringing in instruction, using it in the circuits, and so on and so forth. How will that happen? That is a subject matter of concern for the electronic engineers. But that's a different course altogether. We'll obviously not bother about this in this particular course. It's a thing of interest, but it's a long, big course in itself. So there is no scope for us to cover that. But this is what it is. Okay. Now we come last topic that I'm going to cover today is the concept of interrupts and interrupt handling. Actually, no. Sorry. I don't think